Let's see, real quick on FreeRTOS history. So back in 2003, originally developed by Richard Berry, roughly 2007, Real-Time Engineers, his company took it over. And then fairly recently, Amazon Web Services. So big Amazon, it had gained a lot of following over those 10 years. From 2007 to 2017, Amazon saw an opportunity to use FreeRTOS to further its interests. And so basically took ownership of it. Richard still has control, to my understanding, of FreeRTOS and continues to work on it as part of the Amazon crew. So still very much active and seeing a lot of innovation, but also you start to see they try to make it very easy to tie into the Amazon cloud as well. But I think they're doing a decent job of not being too evil about it. Otherwise, so why would you pick FreeRTOS? Well, as I mentioned, it's been around for 15, almost 20 years, and it's garnered a lot of support in that time. You can see all of just some of the silicon vendors that are supported on the right there, and even some tooling. But yeah, basically you've got the majority of the silicon vendors sitting over there as supported by FreeRTOS. There's a pretty large ecosystem. FreeRTOS also has some additional stacks that you can kind of put on top of it, as far as like a command line interface stack. They've got an IP stack. There's a number of other things that you might need for your application that just kind of comes up really easily for FreeRTOS. And I think FreeRTOS has this goal of being easy to use, small footprint, and robust. There's a large number of embedded systems. Tend to be a lot of the ones we work on at Dojo 5 too, that are just a little too small for Linux. For Linux, you really need at least a meg or two of RAM, and you need a couple of megs of flash. And getting much smaller than that it's gonna be real tough to run Linux. And that class of computer costs a certain amount of money. And if your application needs to be cheaper, then it gets real tough to run Linux. So FreeRTOS becomes a good choice in those situations. The version history, 8.0 and older, is kind of what I consider legacy and stable. They don't release versions that often. 8.0 is probably 4 years old. 9.0, their big feature there was static allocation, which we'll talk about in a bit when we talk about the API. But it allowed a little more predictability in certain types of embedded systems, allowing us to allocate the memory that's used in those systems up front and kind of be able to prove that you weren't going to run out of memory in the middle of some operation in the field, or in a worst case type of scenario. And then they also added 64-bit support in 9.0. And then in 10.0, they added stream buffers and message buffers. And really, the other big thing that happened in 10.0 is Amazon bot. So that's kind of that's the latest, greatest. They've had a 10.1 and a 10.2, which are kind of point releases internally, but those have largely been smaller changes. So it's kind of the biggest version history, but it is still very actively being developed. Just real high level, when should you not use FreeRTOS? Well, I think bare metal is still best for some applications where you don't even have an RTOS, but my criteria for moving to an RTOS is like asynchronous IO. So you're talking to some chip, some other chip, some peripheral, and it takes a while, and you're going to want to be doing something else during that time. It gets pretty messy pretty quick to do that type of thing in bare metal. And you can use interrupts to some degree to do that, but something like an RTOS helps you a lot in that case, where you can handle that IO pretty easily. If you have strict complex timing requirements, that's another place where an RTOS is really going to make it easy. You could do it in bare metal, but you lose some amount of your hair doing that, and so it just makes it a lot easier when you jump into an RTOS to meet a lot of those complex timing requirements. And then if you just have a threaded software architecture where you say we're going to have multiple different components in the system that are talking to each other and passing messages back and forth, you could do that in bare metal, but why reinvent the wheel? Just go grab an RTOS. I do think too that it's easier to start kind of having a good idea. It's worth a little bit of time at the beginning of a project before you start it, trying to decide if you need an RTOS and just going for it if you think there's a reasonable chance you will, rather than starting bare metal and then having to try to retrofit an RTOS halfway through the project. I would say just go for it. It makes it easier kind of to start. I'd say when not to use FreeRTOS, say cellular support is not strong or existent, really. Even with Amazon's ownership of it and their IoT focus, FreeRTOS is really, has some built-in drivers for Wi-Fi and some stuff for BLE, but not a lot of support for cellular. So if you're on a cellular device, I think there are some better options. I mentioned Embed there. Zephyr is another operating system that we've used in cellular applications. So there are some other better choices, but FreeRTOS still has a lot of applications that it makes a lot of sense for. So where do I get it? FreeRTOS.org or OpenRTOS.net. The fastest way is often to look to the SDK from the chip manufacturer. What you'll get at FreeRTOS.org is like kind of the canonical FreeRTOS distribution, and sometimes it's missing some pieces that make your life a little easier based on whatever chip you're on. For example, STM32 has a CubeMX generator that is really nice, quick and easy to generate a project. If I'm doing an STM32 project and I need it to be FreeRTOS based, I just go to CubeMX and generate a FreeRTOS based project. Or for Nordic, grab their SDK and use FreeRTOS. I'll show you what that looks like shortly. But that's a lot easier than trying to grab it from the canonical FreeRTOS site. I would go to the FreeRTOS site if maybe your chip manufacturer doesn't have a FreeRTOS example, or if you're trying to port FreeRTOS to a new architecture or a new board. In that case, it makes a lot more sense or you're going to have to go to the FreeRTOS distribution. Real quick, features of FreeRTOS, like any RTOS, it has, basically we're doing multitasking here, right? We've got 3 different tasks in that picture, and the task number 1, task number 2, task number 3, we want to simulate the idea that those are all running roughly at the same time. But of course, they can't actually run at the same time, so we're slicing up the time so that each one of them can run at some different stage of the CPU. FreeRTOS has priorities for every task, and so if multiple tasks are ready to be executed, it will pick the one that has the highest priority. It also has round robin prioritization. So let's say there are 3 tasks that all have the same priority and they are ready to run at the same time. It will then time slice and run them a little bit of one, a little bit of the next one, a little bit of the next one, and it will go back and forth. It is preemptive in most configurations, which means that maybe a task isn't done executing, but something else higher priority becomes ready to execute. Preemptive means that then FreeRTOS will jump in and stop the lower priority task from executing and start the higher priority one. So it will preempt, and you can turn that on and off, as well as tickless idle, which means that in kind of a more naive implementation of an RTOS, it would wake up every single time slice, like you're seeing on this graph, T1, T2, T3. It would wake up regardless of whether it had to switch or whether anything was running, or if there was idle. It would just wake up on the dot every single time the tick came along, and that has some battery life implications. Especially in battery powered devices, if it's much better to just stay asleep until you've got something that you need to do, or you get interrupted and to do something. And so that's what a tickless idle does, is it just stays asleep as long as it can until the next time it knows it's got something to do. And so in that way, it's a fairly modern RTOS, and not a lot to be desired. It has a lot of good. Excuse me. Yep. So and then for context switching. So what does it look like when we have to switch tasks? The context switching is architecture dependent, and what happens is the CPU has a number of registers in it, and all CPUs work like this. And those registers need to be saved because it basically represents the state of execution for a given thread. The program counter is another item that needs to be saved. Stack pointer is another item that need to be saved. basically all of these values need to get saved somewhere, and they get stored in like a task control block, which is a block of memory that FreeRTOS uses to manage the different tasks. And so when a context switch has to happen, you save off that information, and then you go grab the information from another task that is the one that's going to start running again, and then you load that into the CPU, and then you let it go. And so that's how we do context switching. Basically, that's pretty much architecture dependent. A lot of people are on ARM cores these days. If you have an ARM core, almost all of them are supported, and you shouldn't have to do any porting work at this level at least. But if your chip architecture isn't supported, then there's a porting guide here that helps you walk through those states. But it is pretty low level stuff. You're typically in assembly and moving the registers around. But it can be kind of fun if you get an opportunity to do that. And then tasks in general. Tasks can be in one of four states. All RTOSes have this type of diagram. Just oftentimes the terminology is a little different. So in FreeRTOS, they can be ready, they can be running, they can be blocked or suspended. And so running, I think we're all familiar with. Blocked means that it's waiting for something. Such as a mutex, a semaphore, or a queue, or something else, some type of, or maybe it's just blocked waiting for a timer to elapse. You know, we've told it to delay for 100 milliseconds, and so that blocks it. Otherwise, as you can see, there are some of the API calls. vtask suspend, we'll put it in suspended state. vtask resume, we'll put it back into a ready state. So, and a task can be basically sits in ready if it's ready to execute, but isn't actually the task that's running right now. So only one task is ever in running at any one time. I also just make a mention here that coroutines are something you'll find in the FreeRTOS code. They're supported but rarely used. There were some architectures supported early on that meant that you had to make a trade-off between tasks and coroutines based on memory, but that trade-off is largely non-existent on most modern architectures. So I haven't really ever used coroutines in anything I've done, and just kind of focus on the tasks because they get the job done. So then jumping into some code, what does it look like to read FreeRTOS code? They have a very specific, very controlled style for how they do it. I have the standard and style guide linked below if you want to look through all of the gory details. But you'll see that they use Hungarian notation and prefixes and upper and lower case. Basically what it comes down to is there are really three different types of things that can be that need names. You've got variables in this case, and variables get prefixed with some lowercase letters. U means unsigned, so that's not too surprising maybe to most folks. X is one that's usually new, and that basically means anything other than a standard type. So X might mean that it's a structure, like a complex type. X might also mean that it's some kind of type that, like a base type, like an enum or something that you're using. P is for pointers, and so we can start to, and then the other big thing is macros or pound defines. These end up all in capitals, for the actual name of the macro, but then you get lowercase prefix again, and here the lowercase prefix actually defines the file that it comes from. So we will find a port.h file that defines this macro. One moment. Thought I had a sneeze coming on. My apologies. All right, so hopefully that helps a little bit. Here we see q overwrite. That's a pound define in the q.h file that tells us that the copy position needs to be overwrite. Yes, in here C means an int type, or what we call a char in kind of more traditional C. There's also a S for shorts and L for long. So hopefully that all kinds of starts to make this code a little easier to read and understand. Here's just another example here. The other one we hadn't gotten to yet was return values for functions. So in functions, when the prefix actually is the return value of the function. So here you can see it returns a base type t, which is a complex type, and so it's prefixed with an x. Up here is a call to a function that says prv, which means it's a pointer to a function that returns a void. So that's what's going on there. So it can get a little, or I'm sorry, it's not a pointer to a function that returns a void. In that case, it's a private function or a statically local, a local function that isn't doesn't have scope globally. If it were a PV unlock queue, then it would be a pointer to a void that's being returned by unlock queue. And here we see a PV over here. There's a variable that's a PV right here. All right, so hopefully that gives you at least some confidence to kind of read through the code, and as we get into the code a little more, we can understand what's going on a little better. So now let's talk a little bit about tasks. Tasks in FreeRTOS or any RTOS are a little different than what you'd write in normal code. You can see here we've got a for loop with 2 semicolons. That is basically an infinite loop forever. Normally, of course, you wouldn't write that in a lot of code, but here that's exactly what we want to do. There's a function that runs your tasks, and all your application code goes in here, and you never expect this to ever exit. In the case that some kind of like abort gets called or something, and it actually unwinds out of the for loop, they do like to put a task delete here just to kind of clean up the task, but this should never be called. And then you can see here we're starting to use the API. Here's our kind of first example of the FreeRTOS API, which is how we create a task. It returns the handle for the task, which is a complex type. That's why it starts with X. And we pass in a number of things here. A function that implements the task, and that in this case, vtask code would actually be this function here. We can give it a name, which is mostly just used for debugging, and will show up in some of the debug messages if we'd like it to. The stack size, this one's important, and I find that often problems that we run into with FreeRTOS have to do with exceeding the stack size, setting these stack sizes too conservatively. And then there is a hook that we can hook up that will alert you that a stack overflow has happened, but it is often not implemented out of the box. And so then you're left wondering why your device is just not working. And it's because the stack has been overflowed and you don't have a debug hook for that. So we can optionally pass parameters into the function. You can see the function prototype has to take a void pointer as a parameter. And that is the one and only parameter. And you can do with that what you want. Many tasks just ignore that void parameter, but where it's really useful is, let's say you have the same function, maybe it's handling a serial port, a UART, and you want the same function to run against three different tasks running against 3 different instances, because you have 3 UARTs and 3 different serial ports. You can duplicate and copy paste the function 3 times, but please don't do that. Instead, what you can do, which is much better, is to pass in a parameter, like for the first task you create, pass in a parameter and maybe make the parameter the pointer to the UART instance. And now you can kind of run 3 different tasks with the same code. You don't have 3 different chunks of code to maintain, and each of those threads will run independently, pointing to the correct UART. You also give it a priority. Here they use a macro, and you'll find it in tsk.h, but it points at the idle priority. There are a number of other priorities that you can choose, as well as just picking a number, and I'll show you a little bit about that. And then you get a handle out of task create that you can then use to refer to the task for things like suspending it externally, or deleting it, or changing its priority, some other things like that. And then just kind of a quick overview of all the task APIs. Task create, task delete. You can delay inside of a task. You can ask a task what its priority is, set its priority, suspend it, or resume it. And we'll see this pattern in the different APIs for FreeRTOS, but there are a number of APIs that have static counterparts to them, and then there are also a number of APIs that have from ISR counterparts to them. And for the majority of applications, you're probably going to use the ones that are neither of those. But as I mentioned, they're in FreeRTOS 9, they added the ability for these tasks to have a, or for the entire operating system to run with static allocation only. And so what that allows us to do is to have all of the memory accounted for at compile time. And it's basically, it's a safety measure to make sure that, you know, in some complex call tree that we wouldn't run out of memory. Some systems you need to be able to prove that. So the static analysis allows us to do that. So if you're running in a static mode, you'll need to be calling the static versions of these APIs. But they take exactly the same parameters and they work exactly the same. It's just depending on how you've configured your RTOS, you'll need to choose the correct version. The other piece going on here is from ISR. So when you run the regular task resume, you are not allowed to run that inside of an ISR. And the larger idea here is that inside of an ISR, you're somewhat limited in what you can do. This is an interrupt service routine. And oftentimes the right thing to do inside of an interrupt service routine, especially if you have an RTOS running, is to just set a mutex and get out. Basically, when the ISR is running, all of the rest of the threads in FreeRTOS are stopped. The scheduler is no longer working. Like basically, interrupt handlers on your chip will preempt everything that FreeRTOS is doing, and anything scheduled as a task is completely stopped. And so it's kind of you know, usurping the whole chip when it's running. And so like if you have like complex timing requirements or whatever that need to be handled inside of FreeRTOS, you need to be in you need to be just get in and out of these interrupts. And so that's what the from ISR version is doing. It basically ensures that these tasks don't block, and it also ensures that there's some things that have to happen with the chip architectures to make sure that can run properly from within an ISR versus outside an ISR. Like for instance, we don't want to reschedule a bunch. If task resume means that you know, a new high priority task is going to suddenly go to the ready state and possibly even the running state, we don't want to do that from within the interrupt context while the interrupt is running, because that could take a little bit of time. So this helps us kind of like defer that action until we're kind of running in a more normal context and get out of the interrupt. Let's see, so kernel control, there's a number of other ones that are under kind of the kernel control category, but almost the only one you'll ever use is this task start scheduler. We'll see that in the example code. It's basically, in your main function, your code still has a main and it will run all the setup stuff, and then you call this and this should never return. And at that point, FreeRTOS takes over. So not a lot, and you can see it returns void. So nothing you really do other than you just call it, and FreeRTOS starts going. Queues. So queues are a pretty basic RTOS functionality. When you've got multiple tasks, you often need to share data between them. In some cases, people attempt to use like global structures to share data, and if you're very, very careful, that can work. But in most cases, that causes what's called reentrancy problems. And so, you know, tasks need to talk to each other, need to make sure that need to have a way to know when data is available. And queues are a great way to handle that. Queues hold a structure of data, and your function can call queue receive, and it will block on queue receive, and it will just sit there, and it will actually go into the blocked state, which is great from a battery perspective, because then your device isn't chewing up, it's not sitting there looping and looping, waiting for something to go into the queue. It just goes into the block state, lets our FreeRTOS know that it's going into a block state, and then FreeRTOS knows that it's blocked on a particular queue. And then when somebody comes along and calls queue send and sends something to that queue, FreeRTOS knows then to unblock the task or tasks that are blocked on that queue. And now that because they become ready to run at that point. You'll see that queue create also has a static counterpart, and receive also has a from ISR counterpart. And this one is not allowed to block. So you basically you grab something from the queue inside an RSR, or you get back a return value that says, sorry, there's nothing in the queue, but you don't get to just sit there forever when you're in the ISR. There are others for queues as well. These are kind of the main ones for queues, but there's a link if you want to go look at them. And then you got semaphores and mutexes. Used to signal your task. They're very similar to queues, but without the message data. You'll see that mutexes are just a subset of semaphores, or a particular kind of semaphore. But they've got binary semaphores, which basically either you take it or you give it, but you can't take it multiple times. You've got counting semaphores, which you're actually able to count how many people use the semaphore. And then you've got mutexes. A great example of when like a counting semaphore makes a lot of sense is like for power handling and clocks. Let's say you've got a clock, and the idea here is that in a microcontroller, you only want to turn the clock on when something needs it because it uses up battery. And oftentimes a single clock is used by multiple different users. You'll turn on one clock, and it might be the USB and the UART and the serial port all use that, can use that clock. And so you would take a counting semaphore when you started up the USB, and then you'd take a counting semaphore again when you started up the serial port. And now the counting semaphore would be set to 2. And so then the great thing is, like, when you turn off the USB, then you give up this counting semaphore, and now you can check, is it at 0? Are there 0 users of that clock, or are there still other people using it? And basically, if there are 0 users, you can go ahead and turn off the clock, save yourself some battery. But if there's still some users left, then you know not to do that because they are still using it. And you'll see there too, we've got, again, static counterparts and then from ISR counterparts. They're important. And that kind of takes us through the FreeRTOS API and just high level what, typical things where you interface with FreeRTOS. It's with tasks or with data passing and message passing between those tasks. So now we're going to jump to just the specifics of the chip I chose just to demo on for today. It's the Nordic FreeRTOS port. I'm using NRF SDK 16.0. The 16.0 has all kinds of examples, including a lot of bare metal examples. But they do include in their external directory a FreeRTOS version. It's based on FreeRTOS 10. They have made a few changes to it to accommodate the Nordic chips. And there are several examples that we're going to run to today to just kind of show off how you might incorporate FreeRTOS into design and what that looks like. All right, so let's jump to the Blinky demo. So here I've got Nordic's SDK pulled up, and I'm running it inside of Sega Embedded Studio. This is a free environment if you're working on a Nordic chip that you can debug via a license that Nordic has bought out for worldwide. So when you start up this tool, it will ask you, are you using a Nordic chip? And if you are, great. And that comes in nice and handy for debugging. Otherwise, I typically use Visual Studio Code, and I'm going to show you how that is a pretty decent environment as well if you don't happen to be working on a Nordic chip, and do debugging in there with FreeRTOS and everything too. But let's start here. So luckily, so this Blinky example is pretty simple. We do have FreeRTOS.h included here. That is the one and only header file that you really need to include when you're working with FreeRTOS stuff. That's the intention, is that you only include the one. And then we'll just scroll down to main to start. This stuff is largely, if you're not familiar with Nordic, this stuff is largely boilerplate. But here's where we start getting into something FreeRTOS specific. So here we're creating a task. The task is going to be based on this particular function, which is LED toggle task function, which we find up here. And again, it's a void, taking a void parameter. You can see we don't use that PV parameter at all, and that's just fine. You don't always use it. And we're calling that thread LED 0. We're basing the stack size on the minimal stack size plus 200. And And there's obviously a config, and this is the one situation where it's not actually config.h, but I'll show you. It's actually a file called FreeRTOS config.h, and this is where you configure all of the FreeRTOS settings, really. FreeRTOS use RTC and SysTick are really Nordic specific stuff. It has to do with that which timer is used for FreeRTOS. So I'm just going to skip those for a second. But this is like the block that you'll see on just about any FreeRTOS port. All of these FreeRTOS is designed to be very configurable, and that'll, especially in embedded systems, that's really nice because you can turn on and off things that you don't want or need. And configure it to kind of be the smallest it can be for your application. And so you'll see like tickless idle. This is where we turn that on and off. Preemption. This is where we turn that on and off. And then I've got, let's see, maximum priorities, 3. So 3 is the maximum number of priorities that we're able to support. It's very easy to just adjust this. FreeRTOS, I think, allows you up to 32, so you can get pretty complex with your priority structures if you want. And then minimal stack size, 60 bytes is what we've chosen here. Pretty small, and often, as I mentioned, I see folks setting this fairly small and then get themselves in trouble because the stack overflows. So that's just one thing to really keep in mind. The heap size is the amount of dynamic memory that you're able to find. So if you do a malloc inside of a thread, or if you, basically do all of those kind of like heap allocations inside of FreeRTOS, that's where that comes from. Task names, so LED 0 when we use those quotes. And you can see they're really allowing you to kind of tune this down to how many bytes you want to use here. Do we have mutexes? Do we use the recursive mutexes? Do we use counting semaphores? So all of this can be turned on and off and really configured. Here you see config check for stack overflow, set to 0. That's what I see so often. So, if you set this to 1, you have to add a hook to handle the case where you do see a stack overflow. We'll do that in a little bit, but for now, just know that that's a really valuable one if you're working in FreeRTOS. Yeah, you see co-retunes are turned off. As I mentioned, we don't typically use those. And then a number of other kind of smaller things here that don't really, you can look through, I guess, if you'd like. Yeah, here they even allow you the ability to include or not include certain support or certain header files, which, as they mentioned, most linkers will remove these anyway, so I wouldn't worry too much about that. But yeah, that's largely the rest of this file. So it kind of just allows you to configure all of the FreeRTOS kind of settings pretty granularly. So we got minimal stack size plus 200, so we're giving ourselves some stack for that blinky. We're not passing in a parameter. We're setting it to priority level 2. And this is the handle that we're just going to kind of remember that, task by. Here we're starting another one, and we're calling it LED 1. I'm sorry, we're starting a timer that we're calling LED 1. And then we're starting this timer, and this is just to kind of show off another LED blinking at the same time. So we're showing off really here that we can run a task blinking an LED while at the same time having a timer blinking a different LED. So it kind of shows that not only can we run tasks in FreeRTOS, but we can even mix and match stuff. And then here's our friend vtask start scheduler. This is where FreeRTOS takes over. And then they've got a while forever loop, basically, just in case this were to ever return. We wouldn't go into undefined state by returning from main, but we don't expect this code to ever run. So that's largely what we've got there. Let's run it. Let's see what happens. So if we build this, I had built it before. We're done building, and then we can go run. All right. And here we are sitting right in front of main. We'll see that we can step through this code. And once we dive into here, I'm just going to hit run. And now what we see, and I'm going to turn on my camera real quick. Hello. And on this dev kit, we can see that we've got one LED blinking slow and one LED blinking quickly. So we've achieved FreeRTOS in a quick blinky demo. So now we can we took a look a little bit through this just to prove to ourselves that we know what's happening here. If we look back at the toggle task function, we've got the while true that we expect inside of a FreeRTOS task. It calls invert to invert the LED, so it turns it on or off, whatever it needs to do, and then delays a certain amount, a task delay. Task delay is set to 200. That's the fast blinking one. If we set it to 500, should go a little slower. Let's run that. All right. And we're stopped on main, but here we go. There we go. So now we're running quite a bit slower. And now we're an integer multiple of the other one. So we're kind of show a little pattern there. So yeah, so that's pretty exciting. I think I wanted to dive real quick into the task creation here and just kind of show what's happening there as we kind of like dig into what is FreeRTOS actually doing here. So let's jump into this function. So now you can see we're inside of tasks.c in FreeRTOS. And we can see that TCB is being allocated, what we call a task a control block. And that TCB, if we go to the definition of that, has a number of things in it. And the code gets a little tough to read because everything is configurable, right? Based on those config settings that we saw in FreeRTOS config, things get included or not included in the task control block. You can see ours is a fairly simple task control block. We've got a state list item, so an event list item, a priority, a stack, and a task name. And those should all sound pretty familiar, especially the priority. The stack is our own stack for our task. It holds variables that get created inside of like local variables inside of functions, as well as anything that gets allocated on the stack. And then we've got these two list items, and these have to do with tracking what the thread is or what the task is waiting on. And then we've got this pointer to the stop of the stack. Since we have mutexes enabled, it brings in some other things that have to do with priority inheritance, which has to do with if we're a low priority task and we are holding a mutex that a high priority task wants. In effect, we are a low priority. We can become a low priority task that's blocking a high priority task, and a lot of times that will violate timing requirements for a system. You set a high priority task at a high priority for a reason. It needs to get the CPU. If we're a low priority task that's holding that, some mutex that the high priority one wants, then we get priority inversion is what the issue is called. And so then priority inheritance is envisioned as the mechanism to fix that. And so what happens is, the low priority task temporarily gets the priority of the high priority tasks. So, maybe we're at priority number 0, right? Like the idle priority, and we're holding a mutex that a priority number 3 task wants. Well, our task will be bumped up to priority 3, so it can run as fast as the higher priority task is really allowed, and finish up doing whatever it needs to do to get rid of that mutex, and then the other task can run, and then we can go back to our base priority. So this just allows it to remember what was our base priority, and then remember if its mutexes are held. And test notifications, notify state. And so, yeah, that kind of takes us through that task TCB. Let's go back to Where's my back button? So let's see, that's create static, which we haven't enabled. And not create static, let's just do create, there we go. So there's task create. So we're creating that new TCB. There's a number of things again here that we aren't using. And then there's some stuff that we are. So we do a malloc, and this is whenever you see PV port, that is stuff that's coming from the specific port for the chip that we're using. So malloc in this case is specific to the Cortex-M4 chip that we're using. And it allocates a specific stack for this task, remembers that. It allocates space for the TCB out of the global heap into the TCB, and then and then saves the stack to that stack piece. So we're kind of preparing to get this thread to run, and then it calls a private function called initialize new task, which is here in the tasks.c file that kind of gets it all set up, ready to go, and then adds it to the ready list. So this is a list that the scheduler inside of FreeRTOS keeps to have a list of all of the tasks that are ready to run at any given time. And at that point, if everything has run successfully, we're ready to return pass. Otherwise, the way that this function can fail is if it couldn't allocate the required memory. Perhaps you tried to initialize a task with a very large stack, a stack that the chip didn't have memory to allocate. So, and that's what would happen. But otherwise, initialize new task, we can kind of jump into there. We've got a number of different items happening here. I think the main thing here is, well, here we're storing the name in the TCB, storing the priority, and setting up the mutex related base priority and how many mutexes does it hold, and then saving it to the list. And yeah, and that's basically once we're done with that, then the task is all initialized, the task control block's all initialized, and then we're ready to add it to the ready list, which is part of the kernel. Oh, and I hadn't indexed the whole thing. So there we find it here. And we go into a critical section, which is another useful macro that you'll find both inside the FreeRTOS code, but you also can use inside of your functions. And that will turn off interrupts, turn off the task scheduler as well, so that you're not going to get interrupted during this time. This is non-reentrant code because they're messing with a list of items. And basically, if this is the first task created, they have to do some initialization. Otherwise, they basically add the item to a list, and yeah, and then you're ready to go. Then the scheduler is ready to go. So hopping back to main.c, so that kind of gives us a little bit of an idea what's happening when we create a task and when the timer started. Largely the same stuff is happening there. And then we got a FreeRTOS. Let's jump over to the HRS example. That's kind of the next thing on the list. Let's see. Actually, you know what? One thing I want to, based on our time, I think I'm going to jump into the debug real quick and just show you what it looks like when we've got multiple threads running. Let's adjust this task just a bit. Let's make another task. Let's call it LED2. This is going to call the same toggle task function, and this is where we can show how to use that parameter. So right now, it's hard coded to always blink LED 0, and what I'd like to do is have it blink a different type of basically be able to pass that in as a parameter. So the LED that you want to blink. So we can pass in instead of, so if I change this task function to take an LED and then pass in the LED, and this function needs it to look like a uint32. So I'm just going to kind of just cast it to a uint32. So I'm going to kind of abuse this pointer, but this gets done a lot. Or you could make a structure to pass in and then send the LED as a member of the structure. This gets us the job done pretty quickly though here. And now we can send BSP board LED 0 for this particular one. But then we can pass board LED 1 or board LED 2 here. And that will, and we can see board LED 1 is the one that the timer is calling. So now we'll get 2 tasks running these different LEDs, and then we'll get a one timer task. We could also, yeah, we would probably, if we wanted to do anything with these handles, in this case, we're not really doing anything with these handles, but we'd want to make a different handle for each of these threads so that we could get back to them if we needed to, stop the threads, suspend them, start them up again. In this case, we'll just create another one just so that we look nice. All right, and then so now we will be creating two tasks and 1 timer, and we'll see 3 LEDs blinking. We'll have to build the project. All right. So, oh yes, yeah, now of course we don't have an unused parameter PV. Yes. All right. So, and we have a breakpoint set. There we go. So now what we've got is 3 LEDs blinking. 2 of them are blinking at the exact same rate, right? So those are our 2 threads running, and they're basically running at what is pretty much looks like exactly the same time. And one of them is still the timer running at that slower rate. We could make this even more interesting by running the 2 LEDs at different rates, but this kind of gives you an idea of what's going on. Those tasks are going between ready and not ready pretty quickly. If we hit pause, so this is a really interesting, this is where we can start to see some differences in how you view these things. There is a, let's see, debug options window, tools, where are we at? View, threads. Aha, and I've got to go grab the script. So there is a script that allows you to, it's a JavaScript script that allows you to find the, and I'll add the link to the slides here. But it allows you to investigate FreeRTOS stuff that's inside of, from inside of Seger and get through the threads. And I don't have that set up right now, so I'm going to have to do that after we jump through the. I don't think we're going to have time, so I'll have to do that when we jump through, or when I shoot out the slides. The last thing I wanted to get through here is kind of show off what this looks like from VS Code, because we can actually get this set up to build and run for us. So if I drop us into, and I just, for anyone that's not running Nordic, you either got to have a Seger license or you're going to probably be running from the command line and something like this. So I just wanted to kind of show off what this looks like. We've got examples, peripheral, blinky, FreeRTOS. So this is where we are. If you haven't used Nordic's SDK before, the way they organize their project files is based on the dev kit. We're using dev kit 10056. So I'm going to jump inside of there, and 5.6 has the configuration files for ARM GCC, which is what we're going to be using. Previously, I was using the config files inside of, or the project files inside of Seger Embedded Studio. But we'll be using these for now. So I can be inside of here and do a make. Yes, but this, and yeah, for those who haven't set this up, there is a file under toolchain, components toolchain, that needs to be pointing to your local computer's GCC instance. I will grab that real quick. So mine happens to be sitting in user local bin. Once you've made that change, oh, whoops. What's a trailing? The trailing slash. Now we can make the same Blinky example that we had been making before. Yes. And now it's actually a little bit pickier about us passing that LED value through. So it's saying passing argument 4 of x task rate makes a pointer from an integer. Yep, so we just need to tell it we really meant to do that. Void star here. We got away with it in Seger. All right. There we have our build. They provide any NRF JProg program under our build directory, NRF 52866 hex. That'll program it, and then we also have to tell it what which write, and there we go. So I guess with that, we're out of time. I'm happy to answer any questions if you have any questions. Otherwise, feel free to reach out on LinkedIn or email. Email at hello@dojo5.com, as well as email versus, as well as yeah, any other way. Do you know, so I see your question, thanks Jenny. Do you know if FreeRTOS has been used for devices in highly regulated industries, such as medical? Yes, it has. I think it depends on your QMS system. We have used it in medical devices, we've used it in class 3 medical devices, which are the highest class. It depends on your QMS system, whether you're going to be allowed to use FreeRTOS proper. There is also a kind of like a certified 13485 or 6304 version of FreeRTOS that's called SafeRTOS. You're going to end up paying money for that, but as you do with most things with medical devices. But yeah, SafeRTOS. Go check it out. I don't know actual prices on it. I think it's one of those things that you get a quote, but it's basically it's FreeRTOS under the covers, but they just provide that safety certification. And here's the site if you haven't seen it before. But yeah, it's FreeRTOS under the system. Everything that I've shown here directly translates to that. But yep, you pay money. or if you can get your QMS system quality management group to agree, with the risks of FreeRTOS, you gotta list it as soup and all of that fun stuff. But you can produce a device with FreeRTOS. Any other questions? All right. Well, thanks so much for your time today. I really appreciated it. And again, any further questions, feel free to hit me up. And thanks so much. Have a good weekend.